Hey everyone, and welcome to This Explainer. I am so incredibly pumped to be your guide today because we are going to take some of the most intimidating, buzzword-heavy concepts in artificial intelligence and make them crystal clear. If you have ever felt totally overwhelmed by all the tech jargon floating around lately, trust me, you are in exactly the right place. Today we're going to demystify these complex AI concepts step by step. We're going to break down the actual mechanics, look at the math in a completely approachable way, and give you a rock-solid understanding of what is literally happening under the hood.
Let's be totally real for a second. Even if you follow the tech industry pretty closely, have you ever felt just a little bit of FOMO when people start throwing around terms like LLMs, neural networks, or backpropagation? It is completely normal. The field of AI has exploded so fast that terminology that used to be locked away in isolated research labs is now just part of our everyday conversations. But don't worry, we've got a highly structured visual solution today that's going to get you speaking the language of AI with absolute confidence.
So, here is our game plan for today. 1. Demystifying AI jargon. 2. AI as a master chef. 3. Inside the neural network. 4. Grading the AI test. And finally, 5. Training versus taking tests. Let's just jump right in.
All right, Section 1. Demystifying AI jargon.
You know, Steve Jobs had this famously beautiful metaphor where he called the computer a bicycle for the mind. And it's so true. Computers are these incredible tools that create massive leverage for our thinking. But historically, they relied 100% on human instructions. We had to sit there and write out the explicit rules and code for literally everything. AI, though? AI introduces this absolute dream scenario. Researchers basically asked, what if this tool could figure out its own instructions just by observing us? Kind of like how a baby learns. So we're shifting from meticulously instructing a machine to asking it to learn through observation. Moving on to Section 2, AI as a master chef.
Okay, let's bring those massive buzzwords down to earth a bit. Think of machine learning as literally the art of cooking itself. It's the overarching technique that lets a computer system learn and improve from experience without us explicitly programming it to do so. It's learning the craft. A machine learning model, then, is essentially a highly refined recipe for a very specific dish that's been perfected over time. And when we talk about a large language model, an LLM like GPT, we're talking about the master chef. This is a system that has studied and practiced countless recipes, techniques, and cuisines. That's what allows it to innovate and mix things together in such incredible, surprising ways.
So, if our LLM is the master chef, what exactly is the chef cooking with? Well, that brings us to tokens. A token is basically just a unit of text. It could be a whole word, a tiny part of a word, or even just a punctuation mark. To keep our whole cooking analogy going here, tokens are the raw ingredients. Just like a dish is a combination of different ingredients that build flavor and texture, a sentence generated by an AI is just a clever combination of tokens that build overall meaning.
Which brings us to Section 3, Inside the Neural Network. A neural network is a specific type of machine learning model that's actually inspired, very loosely I should say, by the human brain. Imagine you take a massive kitchen staff of chefs and you organize them into rows or teams. In AI, we call these rows layers. The data first comes into the input layer, basically the starting line. That data is then passed off to the hidden layers. These are the chefs doing the actual deep thinking and processing, almost like a relay race. So the first row might look at basic portions, the next row analyzes texture, and so on, passing their findings down the line until they hit the output layer. And that output layer serves up the final prediction.
Let's say we were building a neural network to predict someone's gender based purely on physical attributes. Our input data might look something like this. We'd feed in Alice's weight of 133 pounds and her height of 65 inches as numerical inputs. These raw numbers are the initial ingredients handed over to the very first row of chefs in our network. But how do those chefs actually know what to do with those numbers?
Okay, stick with me here, because that brings us to the fundamental math of a neuron doing what's called a feed-forward pass. Please do not let the math scare you. It is genuinely so simple. The neuron takes the input we just talked about and it multiplies it by a weight. A weight is just the chef deciding, hey, how important is this specific ingredient? Then it adds a bias, which is basically just a baseline adjustment. Finally, that total sum gets run through an activation function just to keep the final number neat and predictable. A lot of times, it just compresses the number between 0 and 1. And boom, that final number is the output that gets passed along to the next layer.
All right, Section 4, grading the AI test.
Picture this. You just completely guessed your way through a math test, and you get your paper back covered in red marks. Ouch, right? But in AI, that red ink is actually incredibly valuable feedback. Calculating exactly how wrong a prediction is involves finding something called the mean squared error, or the loss. Once the AI knows its error, it uses this brilliant algorithm called backpropagation. Backpropagation is basically the network staring at that red mark test, calculating the exact size of its mistake, and then working backwards through all those layers of chefs to adjust the weights of its connections.
So it's this very literal step-by-step process of learning from mistakes. Step 1, look at the final error. Step 2, trace backwards through the network's thinking. The math here relies on the calculus chain rule to figure out exactly which layer messed up and contributed what to that final error. And step 3, make these tiny, fractional adjustments to the weights so that next time the prediction is just a little bit closer to being right. And it does this over and over and over again.
Finally, Section 5. Training versus taking tests.
Okay, this right here is the grand aha moment of artificial intelligence. We absolutely have to separate training from inference. Training is like studying for the test. It requires looking at billions of examples, doing all that heavy backpropagation, and adjusting millions of weights. It is incredibly slow, and it requires thousands of powerful GPUs running non-stop for months. But inference is just taking the test once you've already studied. It's a single, lightning-fast forward pass of that simple math we looked at earlier. No backpropagation required at all. And that is exactly why training an AI is a monumental, hugely expensive task, but actually using ChatGPT on your smartphone happens in milliseconds.
Just to put that training phase into perspective for you, consider this absolutely staggering figure. Training a model like GPT-3 cost an estimated $4 to $12 million in compute costs alone. Because you can't just skip examples, the network needs to see all of them. This requires massive warehouse-sized data centers filled with specialized hardware like GPUs and Google's Tensor Processing Units, or TPUs. We are talking about consuming enough electricity to power hundreds of homes for an entire year, all just to repeatedly tweak those numerical weights.
And the reason it takes that much hardware is the sheer mind-boggling size of the network. A parameter is effectively a weight. It's the memory of an adjustment the network has made. To give you some scale, GPT-1 had 117 million parameters. GPT-4, on the other hand, is estimated to have an unfathomable 1,700 trillion parameters. Just imagine having to grade a test with 170 trillion questions on it, adjusting the grade for every single one of them millions of times over. That is the multi-million-dollar scale of backpropagation at work today. It's wild.
I want to wrap up and leave you with this incredibly powerful quote from the philosopher Ludwig Wittgenstein. The limits of my language is the limits of my world. By decoding all this jargon with us today, from master chefs and tokens to neural networks and backpropagation, you've dramatically expanded your AI vocabulary. You actually understand the language now, and you know the core mechanics of how these systems think and learn from their mistakes. So the big question is, with this newly expanded vocabulary, what new worlds and applications can you imagine building? Thank you so much for joining me in this explainer, and definitely keep exploring.